Hello guys, this is the fourth video for the hydrocarbons. So we're going to continue with chemical properties of alkene. So now, showing to you right now here is the mind map for the alkene. So we are going to have a look at a few reactions involving alkene, where we are going to have a look at how do the first one, which is the hydrogenations, take place. Okay. And we are going to have a look later on how halogenation is carried out. We're also going to have a look on how hydrations is carried out, and hydrohalogenations, oxidations by using cold dilute conditions, and also oxidations by using hot and concentrated. We're also going to slightly have a look on how alkene is prepared. So however, we won't be able to focus on this one because sooner or later we are coming back for this one. So just a general statement by stating that you can prepare alkenes from sodium hydroxide in ethanolic, and also concentrated sulfuric acid in under reflux, or alumina under reflux by using alcohols. Okay, so we'll have a look at these following tables where the reaction shows how alkenes can be prepared. So the reagents in here is sodium hydroxides in ethanolics under reflux. Okay, so where this reaction will yield two products, okay, according to Sayzev rule. So what is the Sayzev rule? So Sayzev rule I'll explain later when we have reached this haloalkenes topic. Okay. And also dehydrations can also dehydrations by using concentrated sulfuric acid in excess, heated under 180 degree. So you also yield two products, okay, according to Sayzev rule. Or you can even use alumina heated at very high temperature, as high as 350 degrees Celsius. So you also similarly yield two product. According to Sayzev rules, which we shall explain at the end when we touches the alcohols parts later. Okay, so this is how we prepare alkenes generally. What we're going to have a look next in how is the chemical reactions of alkene. So all of these reactions we're going to look into details. So we're going to have a look at hydrogenations of the alkene, where hydrogenation is also via electrophilic additional reactions, and then we're going to have a look at hydrohalogenations, where hydrohalogenations is also via electrophilic additional reactions. We're going to have a look at the halogenations of alkene, also via electrophilic additional reactions, and hydrations of alkene, similarly via electrophilic additional reactions. Oxidations of alkenes, where you have the two different conditions. One is under cold dilute, and another one is using hot concentrated. And last but not least, we are going to slightly have a look at ozonolysis of alkene. Okay, so these tables has generally summarized of what we are about to learn later, so you might want to have a good look at it while we are going at it. So I'll just briefly go through. So generally, when alkene react with hydrogen catalyzed by nickel under reflux, you form alkane, and then if you react with hydrogen halide, you form two different products according to Markovnikov. So what is Markovnikov? I'll shall explain later. We're also reacting with the halogens to form a dihaloalkane, and then you have hydrations to form alcohols at two different products according to Markovnikov rules. And we also have oxidations under cold dilute by using acidified potassium manganate. You form a diol, and when it is under hot concentrated, you form a carboxylic acid, carbon dioxide, and water. So, and last but not least, under ozonolysis, you form a carbonyl compound. So we're going to have a look one by one later of all these reactions, so stay tuned. So first of all, we're going to discuss with hydrogenations of the alkene. So hydrogenation reactions is an exothermic reactions, where this exothermic reactions is carried out at where hydrogenations of alkene, when react with the hydrogens, you form an alkane. So for example, in these equations here, you have propene react with hydrogens, you form propane, and this will release the heat of negative 124 kJ per mole. So note from the reactions that it is highly exothermic. However, the reactions occur slowly as the rate of reactions is low. So Therefore, hydrogenations must be carried out under a mixture of alkane over a finely divided transition metal as catalyst. So there are two general catalysts which can be used for hydrogenations. Recommended are platinum, and if you use platinum as catalyst, you can even react under room temperature pressure. However, if you use a slightly cheaper catalyst, which is nickel, you require a heating at temperature as high as 180 degrees Celsius. Okay, so both of them will give the reactions of hydrogenations faster and more effective. Now, what is the importance of catalytic hydrogenations? So it is often used in food industry, especially in hardening the unsaturated fats and oil to make margarines. So we know that unsaturated hydrocarbons are too soft for commercial use, so that's why you have to undergo hydrogenations in order to create a saturated hydrocarbons. Okay, so this is generally about the hydrogenations of alkene. So finishing the hydrogenations of alkene, we're going to have a look at the second chemical reactions, which is hydrohalogenations. Now, one of the original experiments that is carry out the hydrohalogenations of alkene is done by Vladimir Markovnikov, a Russian scientist to investigate the addition of hydrogen bromide across many different alkene. So in one of the example, he studied that when put one in react with hydrogen bromide, so it will yield two different products, namely 2 bromobutane and 1 bromobutane. So in here, 2 bromobutane is described as the major product, while 1 minor bromobutane is described as a minor product. So from the reactions above, he noticed that hydrogen is generally placed at the unsaturated C double bond C positions that already bear a larger number of the hydrogen atoms. So therefore, he named these rules as Markovnikov rule. Okay, so if you look carefully on the number of the hydrogen atoms surrounding that each C double bond C, you can see that this carbon is surrounded by 2 hydrogens, while this carbon is surrounded by 1 hydrogen. So according to Markovnikov rule, if HBr were to add it with to the alkene, so hydrogens will probably goes to this carbon with more hydrogen, while bromine in the other hand goes to the other carbons and yield this product. Okay. So Markovnikov described these regiochemical preferences in terms of where hydrogen is ultimately positioned. However, Markovnikov observation can alternately be described in terms where halogen is ultimately also described where ultimately the halogen is positioned. So specifically, halogen is generally placed at the more substituted positions in this case. So the similar additional reactions goes with hydrogen fluoride, bromide, and iodide. Okay, so some of these additional reactions are carried out under organic solvents such as CH2Cl2 or CCl4. So we say that rate of reaction of HX increase when going down to the group. So this is due to the bond length, so easier to be broken. Okay, so the mechanism of the reactions can be explained in the following steps of reactions. So starting from the step 1, we have the alkene protonated by forms the carbocation, where the unsaturated C double bond C, okay, will attack the hydrogen in the hydrogen bromide, and heterolytic fission take place in between hydrogen bromide and also hydrogen and also bromine atoms. So you'll form a secondary carbocation. So this is a secondary carbocation, and hydrogen will go to the carbon with more hydrogen in it. And note that this is a slow step where it is a rate determining step, followed by step 2, where the step 2, the negatively charged bromide ion will attack the positively charged carbocations in here. So this is a fast reaction, and eventually this is how you form a 2-bromo-butane in this case. Okay, so these two-step mechanism are very regio selective, and that is why for this case 2-bromo-butane is used as the major product. Okay, in theory, protonations can take place either in a primary carbon or a secondary carbon. So if we look at this if we look into the position of how HX attacks the alkene involved, okay, so eventually when the pi electrons attack the HX, it can be placed at as a primary carbocation, or it can be placed as a secondary carbocation. So generally, with in terms of the selectivity, yeah, okay. So this is the energy profiles for the after when you attack when the protonations take place in as a primary carbocation and as a secondary carbocation. So you see from the reactions in here that these protonations is easier to occur at a secondary carbocation because the activation energy is lower for a secondary carbocation to be formed. So therefore, in terms of stability, a secondary carbocation is to say more stable compared to a primary carbocation. And it comes to no surprise if there is a tertiary carbocation, definitely tertiary carbocation is the most stable. So note from the transition state to form a secondary carbocation is significantly lower than the formation of primary carbocation, which explains why a secondary carbocation, especially in this case here, okay, is preferred to be formed. So evidentially, if a tertiary carbocation is formed, it will be more stable than the secondary carbocations. So here we summarize the stability increase when going down to the classification of the carbocation. So how are we going to explain this stability of the carbocation? So imagine that usually all alkyls behave as an electrons donating group. Okay, so when electron donating groups of the alkyl is attached to that carbon, so it will cause the electron density of that particular carbon increase. So if this is for one alkyl where the electron density slightly increase, if there are two alkyls surrounding the carbon, you can see that the electron density slightly increased further. And if it is a tertiary carbocation where this is actually R, not H here, where this is actually R, okay, so you can see that when the tertiary carbocations take place in here, the electron density are going to be increased much more. So imagine that if you have a great electron density, so the carbocations stay in here is the most stable because where it is rich in electrons. Okay, so that is why tertiary carbocation is to say the most stable carbocation that we have in here. Okay, so hopefully that that helps you to understand why in regioselectivity tertiary hydrogens will preferable to be attacked with carbon with more H's. Okay, so this is all about hydrohalogenations of the alkene. So next we are going to have a look, before that, this is the examples of hydrohalogenations. So if you have a vinyl cyclopentane, when you add it with hydrogen iodide, so either the H is added to here, I is added to here, or you can have the other way around where the H is added to here, where you have this H is added to here, I is added to here. So since this carbon has more hydrogen, so you expect one iodocyclopentane is a major product, while cyclopentyl iodomethane is a minor product of the reactions. Okay, similar to 2-methyl-butyene. So in 2-methyl-butyene, when you expect hydrogen bromide to attack this alkene, so there are two possibilities. Either the hydrogen attack this carbon, bromine attack this carbon, or oppositely, you have hydrogen attacking this. You have this hydrogen attacking this carbon, while bromine attacking this carbon. So since this carbon has greater number of hydrogen, so you expected 2-bromo-2-methylbutane to be the major product, while 2-bromo-3-methylbutane to be the minor product. Okay, so I guess that is all for the fifth video, so I'm going to stop and thank you.